So Unit 8 is on something called thermodynamics. So there are going to be several videos on thermodynamics. This one is going to introduce you to a lot of the terms that we're going to use for the rest of the unit. So first term, obviously, is thermodynamics. So break down the word. What do you see? There's thermo. What does that mean? There's dynamic. What does that mean? So if you haven't figured it out, thermodynamics is the study of how energy changes during a process. So next set of terms we're going to take a look at: temperature versus heat versus enthalpy. And one thing that you need to keep in mind is that in a sample, not all of the particles have the same amount of energy. Some have less, some have more. And so really there's a big distribution of energy that the various molecules in the sample possess. So how do we differentiate between what do we mean by temperature of that sample, what do we mean by heat of that sample, and what do we mean by something called enthalpy, which is probably something you haven't heard of before. So temperature, given the variable T, as you already know. Heat actually doesn't get a variable. I'm not sure why. And then enthalpy actually gets the variable H. You're going to see that heat and enthalpy, especially for us, are very closely related. So temperature, something you're very familiar with after the gas unit. Temperature is the average kinetic energy of the particles in a sample. So we would kind of equation-wise define it as temperature is equal to the sum of all the kinetic energies divided by the number of particles. Makes sense, okay? Heat is actually the amount of energy that's being transferred during a process. So within a temperature gradient. So energy always moves from an area of high energy to an area of low energy. So the heat is how the energy moves across that gradient. That's what heat is. Now enthalpy, equation, heat is really equal to the sum of all the kinetic energy. So not divided by the number of molecules, just the sum of the kinetic energies. Enthalpy is going to seem a lot like heat. It is the total amount of internal energy of a system. Basically, we're going to keep it at that for this year. We can't measure enthalpy of a system, however, because there's no way to get a little probe into the molecules themselves. So what we have to measure is the change in enthalpy. Change in enthalpy means change in energy content. Well, that's kind of what heat is. Heat is how energy is moving from one place to another. And since we're measuring the change in energy, we're essentially measuring the heat change. Delta H, enthalpy change, is really the sum of, I should have had sum in here, the sum of the kinetic energy per mole of reaction. So delta H is always expressed, well, usually expressed as kilojoules per mole. So energy, we use the unit joule, if you remember, to describe that. So the units of delta H are typically kilojoules per mole. So like I said, enthalpy and heat are going to be pretty synonymous for us. And in order to measure the energy change, we actually need to use the temperature change. So these are all three very closely related and are going to help us examine energy. All right, so those are the first three terms. Next set of terms, we're taking a look at different types of energy. Well, you've already learned about kinetic energy. You know from the last unit that kinetic energy is the energy of motion. There are actually three types of motion. There's vibrational, rotational, and translational. And here's kind of a good visual of what those different types of motions entail. So vibrational motion is the most limited type of motion. Notice that we could have a bond angle changing a little bit. We could have a bond length changing a little bit, symmetrically or asymmetrically. But this is a pretty limited type of motion. And you probably can figure out that In solids, the only kind of motion they can have is this vibrational motion, because in a solid, the molecules are really held tightly in place by all the IMFAs. When you start to break some of those IMFAs, then you can have something called rotational motion, where you have the molecules spinning around a particular axis. So rotational motion is what happens when some of the IMFAs break and you create a liquid. And if I break all of the IMFAs and there's nothing holding these individual molecules together like you have in a gas, this is where you get translational motion, where the molecule can actually move from one position in space to another. So all molecules have vibrational. Liquids and gases have rotational, but only gases have translational. So gases have all three types of motion. All right, so the other type of energy that we want to make sure we talk about is potential energy. Back in freshman year, you probably learned that potential energy was stored energy, or I'm sorry, energy of position. In chemistry, it's stored energy or internal energy. And where do you find stored energy? That energy is within the bonds of molecules, or within the IMFAs if you have solids and liquids. So both types of interactions between atoms will involve potential energy. All right, next set of terms is system versus surroundings. And these two are equal but opposite ideas when we're talking about energy change. If a system does one thing, the surroundings will do the opposite. So that's one thing that you want to remember. So for the system, it's usually the chemical that we're interested in, the material that's undergoing the chemical reaction. The system is what causes the change in energy. So it either undergoes a chemical reaction, so it modifies its covalent bonds, for example, or it undergoes a state change and modifies its IMFAs that are holding that substance together. But no matter what, the system is what causes the change in energy, because the system has bonds that are being broken or formed or whatever it is that's going on. The surroundings, you can probably guess, is anything that's not the chemical. So technically, it's everything else, but realistically, it's really only the substances that are close to where the chemicals are. So the container, the water, if the substance is dissolved in water. Water's not part of the system, water's part of the surroundings. The air around the container, and so forth. So again, it's how close is that material to the system in order for it to actually influence what's going on. And the surroundings, the important thing to remember here is that even though the system causes the interchange, the energy change, it's the surroundings where we see the energy change. We observe the surroundings. We can't observe the system. We can't put a little probe into the molecules and see the energy of that system. We can only measure the energy change of the surroundings. So it's really important to remember that, because what you see happening is the opposite of what's going on inside the system. So we have to use what we observe in the surroundings and infer what's going on with the system. So that can be a little bit tricky. We're going to do a little demo in a few minutes that'll hopefully help you see that idea. All right, next set of terms will be the two different types of energy changes that can occur. So you can have an endothermic process, which I know you've learned about in freshman year. And if you remember, an endothermic process happens when energy enters the system. So if energy is entering the system, what's happening to the surroundings? It's losing the energy, right? Because what happens to the system is the opposite of what happens to the surroundings. So we're going to focus on the system here. So an endothermic process is where energy enters the system. So energy is going to be moving from high energy, which is the surroundings, to lower energy, which is the system. And what are you going to observe if this happens? Well, remember that we observe the surroundings. So since the surroundings is losing energy to the system, you're actually going to feel the container get colder. And here is a demo, a video demo that shows that to you. So we're gonna do the reaction between barium hydroxide and ammonium chloride. So those are the things in those two beakers. This is kind of just for impressiveness. They're going to put a small amount of water on that block just to show you what's going on. Now remember, this is an endothermic process. So the chemicals are going to be absorbing energy from the surroundings. So they've mixed the two solids together. They're stirring it really well. Notice what's happening to the beaker. It's getting a little mushy. It's also absorbing a lot of energy from the surroundings. So if you were to measure the temperature of the beaker, it went from 22 degrees to minus 25 degrees. So the temperature dropped. Ignore all those delta changes. The temperature dropped, and where'd that energy go? It went into the system. So that's an example of an endothermic process, the reaction of barium hydroxide and ammonium chloride. Energy left the surroundings, so the surroundings got cold, and we saw that coldness happen because the wooden block actually froze to the beaker. Okay, so the other type of reaction is an exothermic process. So in an exothermic process, energy is exiting the system, energy leaves the system, and if it leaves the system, where does it go? It goes into the surroundings. So energy is moving from the system, which has the higher energy, to the surroundings, which in this case is going to have the lower energy. So what do you observe happening? Since the surroundings are gaining energy, you're going to feel the container get hot, or you see flames, or you see an explosion, which is really pretty cool. Okay, so here is a video of an exothermic reaction. This is called thermite. So what he is doing is he's going to take aluminum solid. It's really fine aluminum powder that he's going to use. And he is going to mix it with iron oxide, which is actually rust. So again, we got two solids getting mixed together. And he's talking, but you can't hear him talk, so I've got to talk over him. So what he's got, he has a flower pot there, and he has the two chemicals in a flower pot. He also has a sparkler. See, there's the solid, and he's got a sparkler there. The sparkler's going to get the reaction started. It's called, so the sparkler being present is kind of like the same thing a match does to light a candle. It's what's referred to as the activation energy. So he's going to light that sparkler on fire, and as the sparkler burns down, the sparks are going to hit the aluminum and the iron oxide that are inside, and you're going to see a really cool reaction take place. And he's going to back away because this thing gets a little dangerous. So right now it's just the sparkler going, but wait, in a second you're going to see the actual reaction start to take place, and it's going to be much more impressive. There it goes. There's the reaction. Look at all that. Isn't that cool? So that's definitely an exothermic process. The reaction is generating a ton of energy. Notice what's happening. Do you see this? What's running down here? That is actually liquid iron. So if you noticed, it was a single replacement reaction, and one of the products was going to be iron and the other product was aluminum oxide. The iron has actually dripped down, become liquefied, and dripped down into the container that's below it. So that's pretty cool, isn't it? So that's an example of an exothermic process, because you see energy being given off from the system. All right, so now I want you to experience something. So here we've got a little activity for you to do. So I'm going to have you pause the video, and then actually I'm going to have you stop the video, and we're going to start it, pick it up on the next one. So you're going to go to your freezer, pull out an ice cube, hold the ice cube in your hand, and I just want you to make observations. What's happening as you hold that ice cube in your hand? And then write down those observations. Okay, so you go do that, and then once you've done it, start the next video, start part 2.